Hi, I'm happy to present my work in progress project about using diffusion models to denoise low coverage RNA-seq. So as we've talked a lot about RNA-seq, I still want to establish the vocabulary I'll be using. So RNA-seq, obviously, we use it to quantify gene expression by taking the RNA from a sample, such as a tissue from a cancer patient. We fragment this RNA and we give it to a sequencer, which gives us our reads, which we can then align to a reference transcriptome. And counting each of the reads for each of the genes gives us our transcriptomic profile. Now, RNA-seq is great. It's very useful. It's also very expensive. Here I put it in Canadian dollars because I don't know how expensive it is here in the US. But the main point I want to bring here is that most of the cost comes from the coverage. That is to say, the number of reads we sequence on average per sample. Even at the lower end of standard coverage of around 20 million reads, it's 3/4 of the price. So we can naturally reduce the coverage to decrease our total costs or increase our sample sizes given a fixed budget. However, this naturally decreases the quality of our data and even makes us lose the capture of certain genes. Now, this is the kind of problem that's observed in single cell or other by nature low coverage technologies. And there are tools that are called imputation tools that exist, but those are made for those specific technologies. And there does not seem to be any applicable to bulk RNA-seq. So is there such a model we could make that could work with bulk RNA-seq for any coverage level? And we think we found it in the denoising diffusion probabilistic model, also known as DDPM. And I'll ask everyone to just bear with me here while I explain. So it's the model that starts from random data or empty data and iteratively generates a new realistic sample using a neural network. These iterations are also known as time steps. Those of you who don't know, well, you actually do, because it's at the heart of a lot of AI image generation tools that exist nowadays, such as DALL-E 2 or Midjourney. And there exists a few versions of the model. The one at the top is the more standard version, which starts with random data and shifts values up and down until we've generated a realistic sample. But it's the bottom one that I'm interested in, that was published recently by Shen and Zhao in 2023. That starts with all zeros and increases counts until full resolution is reached. I don't know if you have the same realization as I did when I saw this, but this is kind of like RNA-seq with all genes that start at 0. And the more sequencing we do, the more our counts are increased for each gene until we reach full coverage. So that's the idea we want to propose. We want to recontextualize this model that's normally generative into one that is for denoising by linking the coverage to the time steps. By doing this, we would train a model, and once that's done, we could find the time step corresponding to a real low coverage sample and pass it to the model and iteratively denoise it until we reach full coverage. So that is at the heart of our project, where we want to do this recontextualization, since we believe that the intermediate time steps contain enough information such that we can denoise to reach the same quality as full coverage. Since this is a work in progress, I'm only able to talk about the first two objectives, which are to set up the data and the benchmarks, and we've started developing the model itself. So first, for the data set, not the first time we've talked about it today, I'm going with the Cancer Genome Atlas, or TCGA, because it's pretty big, over 10,000 samples of pretty standard coverage, it's public, all that good stuff, with a few statistics. And for lower coverage, we're going to use binomial fitting to simulate lower coverage versions of the data set. This is the kind of thinning that was used in the paper by Shen and Zhao. And it's essentially just using a binomial distribution to undersample our counts until we reach our desired coverage level. This allows us to not only get low coverage expression data for no additional costs and pretty quickly, but also lets us correlate our results for low coverage data directly to the results we should get at full coverage, giving us a sort of ground truth, which would be much harder to do if we sequence completely new data at low coverage. Now, having this data, we wanted to quantify the effects of low coverage on information that we can gather from the data set. So here we just decided to go with the ability to predict the cancer type from the transcriptomic profile. And for this, we used a logistic regression because it's a simple, easily tunable model. So we see on the right here that we went from coverage levels from 20 million reads per sample to 200. And naturally, the classification accuracy goes down. Interestingly, we still have nearly 95% accuracy at 20,000 reads and around 90% at 2,000. So the performance stays pretty high for a long period of time. But nonetheless, this sets us up for our baseline from which we want to improve given a denoising. But can we denoise? Well, we'll start with something simple before using our diffusion model. Well, simple-ish. The model, for each of the coverage levels, we trained a unit, or in this case, it's mostly a denoising autoencoder with skip connections. And in orange is the result of the training here. So for each coverage level, we see that either the performance stays about the same, or it decreases the effect that happens when coverage is reduced. So good sign. The denoising can be useful. But as I said, we trained a model for each of the coverage levels, which is not very practical. We'd want a model that can cover any coverage level. And that's where the diffusion model comes in. Now, the architecture is here. It's a little scary, but there's a few things we need to know about it. First, this is essentially the architecture that was used in the paper by Shannon Zhou for non-image data. Second, it's basically just a deep, fully connected network with coverage information injected periodically. And finally, once the model is trained, it's an iterative denoising process, meaning our low coverage data will pass through the model several times until full denoising is reached. So on the right, we have our initial conditions, since we decided to go with starting from 20,000 reads. So we plotted for each gene in each sample its value at 20 million reads on the x-axis and at 20,000 reads on the y-axis. So naturally, the counts are lower, variance is higher, we have dropout with a lot of expression values going down to 0. So if we let the denoising process happen, our counts increase over time and reaching 93% correlation with the original data. Unfortunately, it does look like there's an increase in variance and there's some values that don't increase as they should. But can we still use it? Was there an increase in performance? Not currently. Unfortunately, currently, our model still needs work, needs improving. At least it isn't making the data worse, but we still need to figure out how to increase the performance or increase the capacity of the model. I'm actively looking for feedback or suggestions, so if you have any ideas, please come talk to me. I'd be super happy to learn about your ideas. So yeah, there's just more work to do for now. All right, so that's where we are currently. We have to naturally finish the development of the model and hopefully get everything working. And if it does, well, then we could actually be able to use it in a practical context, such as when our current idea is perhaps long-read RNA-seq, because that is also by nature low coverage. So our main idea here is that these diffusion models are very powerful. They're present in contemporary AI, and we hope we can harness their power for this denoising so that we can reduce costs or increase sample sizes for all sorts of uses, particularly for transcriptome-wide analyses, such as reducing hospital bills or having very, very large cell line analyses for like 20,000 compounds times 1,000 cell lines, which would be the ideal final step that we're thinking in our lab. So I want to give a quick shout out to everybody in my lab, my PI, Sébastien Lemieux, Raphaël Lambert for the prices in Canadian dollars. I don't know what the conversion rate is here. And I want to thank you for your attention.
Suggestions for Carl. So once again, if you either want to take the mic or talk loudly enough and make sure that you're being read out. Thank you so much for the talk, Carl. That was quite interesting. I was wondering if you worry at all about hallucinating in your extremely strong composition of a prior onto data that may be from a different distribution. So, for example, you're doing this on a bulk RNA sequencing data to do some sort of cancer diagnosis. What happens if someone gives you data that just looks very different? Does your denoising model try to make it look like the data that you started from?
That, honestly, if I train it just on TCGA, probably. We will have to either incorporate more data sets or do some sort of data augmentation for it to work properly. But yeah, currently it's probably just going with the averages right now, which once we can get it stuck out of that, then we can look into making sure it generalizes to other data sets. We're actually hoping it can be single cell compatible. Cross our fingers. We'll see if that actually works. But yes, we'll definitely have to look into that.
Can you repeat that question?
Okay, yeah, it's asking if about the differential expression analysis, if the model can consider that and end up having correct analyses. That's part of our benchmarks that I didn't show, and we didn't get to it yet. That's the answer. The answer is we hope so. We don't know yet.
Great.